EMR is a fully managed service that allows you to run your big data workload using open source framework, including Spark, Hive, Presto, and more. It works directly against your data on S3, so you don't need to move or transform the data. And it provides a 100% compliant API with the open source API. So that means you don't need to change your code when you move to EMR. In this session, we will cover the optimization of the features to optimize the cost and the performance. We will cover the runtime optimization, and we will cover also all the features and configuration related to the infrastructure and the cluster management. And then we will cover new features, recent features related to self-service data science with the EMR Studio, SageMaker Studio integration. We will cover new deployment options with EMR and ETS. And we will also cover how EMR can help build your data lake and integrate with different data formats and also support some different security patterns. So let's start with price performance. There are two tenets in EMR. First, we don't break the API. This is very important. It's 100% compliant with the open source API. And then we also provide these performance improvements out of the box, so you don't need to change anything or configure anything. It's natively available. You can see on the right side some of the optimization that we implemented for the Spark runtime. I won't go through all of them. I will just take one example, dynamic sized executor. So without dynamic sized executor, you basically need to set your memory and CPU for your executors, and you need to match it with your cluster configuration, the instance type, instance size. It can be tricky, and you can waste some resources. With dynamic sized executor, EMR takes care of this for you. It will just check the configuration of your cluster and adapt the Spark executor configuration to ensure that you have optimal resource utilization. So with all these improvements, we provide a runtime that is 3x faster than the open source Spark free version, if you compare based on the TPCDS benchmark. And again, very important, you have the exact same code, and you have no configuration to benefit from these improvements. Additionally, if you want to improve more, you can also use different instance type, including the AWS Graviton 2 instances. I will go into the details later, but they provide around 11% better performance compared to the previous generation. So that was for the Spark runtime. We are also extending this optimization to other runtimes, including Presto and Hive. So for Presto, you can achieve 1.87x faster performance compared to the same open source version. And for Hive, you can also benefit from this continuous improvement, the process that we are adding new optimization in each EMR versions. This is a good example of the improvement you can have upgrading your EMR version if we compare 6.4 with 6.3. You can achieve 1.25x faster performance on the geometric mean and up to 2 times improvement on some individual queries. We are doing that optimizing the query planning if you are using AWS Glue Data Catalog. And we are also optimizing the query execution time if you are using ORC-based ORC data format for your S3 storage. I repeat this. Similarly with Spark, Hive, and Presto, you have this 100% compliant API with the open source framework. So that was the optimization on the runtime. Let's move on some new features and configuration that allows you to optimize the infrastructure and also the cluster management. So one of the good improvements that we provided this year working on the startup time, starting an EMR cluster is now 35% faster. We did this working on the task node provisioning alongside the core and master node. And we got 3 minutes of savings of reduction in startup time doing that. We are also now using idle instance in VPC, when you need to provision cluster in private subnet, that's an additional 2 minutes of savings. And we also worked a lot on this integration with the EC2 API to provision your virtual machine, and we optimized the retry mechanism to avoid throttling. That's very valuable for very large cluster provisioning, for example. Another optimization is to use the Graviton 2 instances. These are custom designed by AWS based on the ARM architecture. And they are providing a benefit of 30% in price performance with two different points. The first point is it provides better performance between 12 and 16% compared to M5 instance type, but they are also cheaper, around 20% lower in cost. So that means you can really get these benefits for your EMR workload, and it's natively available. You don't need to change your code or compile code for this architecture. You can just take your code, drop it on Graviton-based cluster, and you will get these benefits. Another big benefit is using Spot instances, but let me do first a brief recap. Spot instances are unused capacity that are offered at huge discount, up to 90% of cost reduction versus the on-demand price, but there is a counterpart. Counterpart is that can be reclaimed with a 2-minute notification. So that means your workload needs to be fault-tolerant if you want to use Spot instances. The idea is you can scale out your workload and increase your throughput, providing more resources, but stay in the budget. And they are very popular because they are very well integrated with AWS services, including ECS, EKS, Batch, and EMR, and also third parties. EMR is a very good fit for Spot instances because, first, big data workloads are scalable. You can just add more resources. Your workload will scale. You will increase the parallelism, and you will finish your job execution in less amount of time. Second, most of the workloads and frameworks are resilient. That means if you have a Spot interruption, you won't necessarily break your job, and it can just recover from this interruption. Especially Spark, which has a great mechanism, a resiliency mechanism. It can just reprocess the data, and your job will continue. So the idea to use Spot with EMR is really to provide more resources, increase the parallelism, increase the throughput of your job. You get these additional resources with a huge discount, up to 90%. And that means you can really massively scale your cluster and process your data in a minimum amount of time. So that means you can also reduce the risk of interruption. That's a very good illustration of this principle. If you have a job that is taking 10 hours to execute, you can just scale out and run it in 1 hour, providing more resources. And let's take this concrete example. So imagine you have a 10-node cluster that is running for 14 hours with a unit cost of $1 per hour per node. That's a total cost of $140. You can scale, add just 10 more nodes. That will reduce the runtime to 7 hours. But these compute resources are also available at a lower cost. So instead of $1, you just have, for example, 50 cents per instance. That means you will also reduce the cost of your job to $105. So finally, you get 50% reduction in runtime execution, in runtime time, and 25% in cost reductions. This table is a good starting point if you don't know when to use Spot or not, and for which kind of workloads and which kind of node. Just a quick recap, the leader node is critical for the cluster. It contains all the metadata, so losing a leader node means you will break your cluster. Core nodes are generally important because this is where you place the critical component of your jobs, like the Spark driver, which contains the metadata. And task nodes are purely stateless nodes that you can use to just scale out very easily and very quickly. So there are two important points on this slide. The first one is for low criticity jobs, you can just use Spot everywhere because you will be able to just reschedule the job in case of Spot interruption. But more important, even for the critical job, you can use Spot on the task node, and that's very important. You can use, for example, the instance fleet configuration of EMR, which really allows you to select some Spot instances and try to minimize the cost of your workload. But in case you have some constraint or unavailability of Spot instances, it can fall back on demand. So you still ensure that you provide the resources to process your job and you can meet your SLA. We have thousands of users and customers using Spot instances with EMR, and one of them is Salesforce. They applied this strategy of scaling out the cluster using Spot instances, and they achieved a better performance. They were able to scale also their analytical workload, and they saved 80% compared to the on-demand prices. Let's now move on a feature that is very useful to manage your cluster and to dynamically adapt your cluster to your workload and also reduce the cost. So EMR users are familiar with the auto-scaling feature, which allows to dynamically scale your cluster based on some metrics. But they needed to define the metrics and the thresholds to configure this auto-scaling. So now we are adding a new feature, which is managed scaling. Managed scaling is a fully managed experience of the auto-scaling. You just need to precise minimum and maximum constraints for your cost. And EMR will manage this auto-scaling for you using a constantly improved algorithm. It will deeply monitor your cluster and your workload to dynamically and quickly adapt the size of your cluster. So using this managed scaling, you can achieve between 20 and 60% of cost reduction. And we are also adding some optimization to this managed scaling. So now the managed scaling is aware of the capacity of Spot. That means it's deeply connected in near real time with the metrics from EC2 Spot. It can monitor the pool depth and pool stability to really select the right instance type and minimize the risk of Spot interruption. If you are using EMR node groups, you can now also use this managed scaling across different node groups to ensure that you are diversifying the instances and minimizing the risk of Spot interruption. Another optimization that we are bringing to this managed scaling is the shuffle awareness. A brief recap on the shuffle data in Spark. Shuffle data is transient or intermediate data that is used for processing your Spark application. And if Spark loses this intermediate data, it needs to reprocess your data starting from a previous state and sometimes from the beginning. So this is a kind of critical component that you cannot afford losing. And now with this optimization, the managed scaling is aware, is deeply monitoring the different nodes and is aware of the nodes with active shuffle data. So it won't decommission these nodes during the scaling phase of the auto-scaling. So that was for Spark. And we are also extending this managed scaling feature to different workloads, including PrestoDB and Trino, available in EMR 6.4. You can sign up for the preview, sending an email to this address. Axiom is one of our customers who is using EMR with Spot. They were able to achieve, to really scale and to achieve grid performance optimization on their inference jobs. They reduced their execution time from 11 days to 15 hours. using this managed scaling and Spot. So that was a brief overview of visualization on the runtime and the cluster management. Let's now move on some new features that we recently added to EMR. And I will start with self-service data science with EMR Studio and SageMaker Studio integration. So EMR Studio is a fully managed IDE that allows your data engineers to quickly build and deploy code. They have this unified interface with all the features required to do their job. They have a fully managed Jupyter notebook experience with lots of integrations like SSO, Git repository, cluster management, debugging tools. All the features that are necessary for building and deploying code are available in this single interface. I will detail them using a very common data science or data engineering workflow, where the first step is maybe to prototype some code. So for that, your data engineers can connect to this EMR Studio interface. This is really a single place with all the features available. They don't need to connect to the AWS console. They can just use their credential, their corporate credentials to access this interface using AWS SSO. And they have access to this workspace where they can provision and manage their workspace. Workspace are a group of notebooks that can share some common characteristics like S3 location for notebook savings, cluster attachments for running the notebooks, or Git repository attachments. And they can create and manage their notebooks using this Jupyter interface. And they can write Python code, R code, or PySpark, or Scala code. But the interface goes beyond the standard Jupyter notebook experience. Okay, we are adding a list of curated extensions that really provide all these features available in this single interface. I will go through the details later. And we are also adding a new feature very soon. Directly in the notebook, you will be able to use the SQL Explorer to run custom SQL queries on top of your data sets. You can see on the left side that you have access to your data catalog. You can browse your database, tables. And on the right side, you can create one or more tabs to just run some queries. The queries will be executed on EMR clusters. We currently support PrestoDB engine with Spark SQL coming soon. So the next step is maybe to set up your environment and load some custom kernel or libraries and dependencies. This is also something very easy to do with EMR Studio. You have two options here. First option is to use the PySpark kernel to provision notebook scope libraries. This is very practical because you don't need to set up your cluster. No bootstrap action to prepare the dependencies on the cluster. You can just install them in live from your notebook. These dependencies are also scoped to your session and only your session. That means if you share a cluster with other users, they won't interfere with their dependencies. And everybody can bring their own versions and preferred library. And finally, it's reproducible environments. That's really interesting because your library's description are in the notebook. That means you can attach a notebook to a different cluster and rebuild the same environment very quickly. The other option is to install libraries and kernels for everybody, for all the users on the cluster. You can also do that using the Python kernel. Single pip command will download and install the libraries or kernels on the master node of a cluster and make them available for all the users. OK, so now your environment is ready. Probably want to collaborate with some peers. You can do that with EMR Studio because you can integrate your notebook and your workspace with a Git repository. We currently support Code Commit, GitHub, and Bitbucket. And again, you have access to the Git command like push and pull directly from the workspace interface. So you can just publish and get some updates from collaborators. So that was offline collaboration. We will add soon the online collaboration in real time. So directly from the EMR Studio interface, you will be able to invite collaborators in your workspace. And then you will be able to work with them, do some live coding session, very useful for peer reviews, live troubleshooting. You will see the change of each other. It's a very nice feature for collaborating in real time. Of course, you need to test your code. So you need to connect to some clusters. That's also very easy to do with EMR Studio. You have 4 different options here. First option is just to connect to a running cluster in your account. So you have this list available on the left side. You select the cluster and you attach your workspace to this cluster. Second option is to create a new cluster with a very simple configuration, like number of instances, EMR version, instance type. For more complex configuration, you can also use templates from this interface. Generally, the templates are created by administrator and published into AWS Service Catalog. And then you can instantiate clusters based on these templates. And finally, you can also run your Spark jobs directly on Kubernetes, connecting to EMR on EKS. When you run your code, you will need to debug. It's an iterative process. You will need to see what's happening in your notebook. That's also very simple because you have a direct link from your notebook to the Spark History Server. It will open a new tab, a new browser tab, and you will have the exact same experience as you have with an history server in Spark. When you are happy with the results, you probably want to move your workload into production, and that's also something that you can do with EMR Studio. EMR Studio has an API to programmatically execute a notebook, and this API is packaged into an Airflow operator. That means you can use this Airflow operator in both self-managed Airflow or Amazon-managed workflow for Apache Airflow to run your notebook into your Airflow pipelines. You can provide parameters, and you can also chain multiple notebooks into your pipelines. We will add soon another feature to run your notebook directly from the interface, from the EMR Studio interface and the workspace. It's a pure headless mode. You will just trigger a job execution with your notebook. And finally, after you move to production, you need to debug and monitor your job, see what's happening. So that's also something you can do directly from this EMR Studio interface. You have a list of all the clusters that are running. You can browse them. You can filter them, for example, by state. And for each of them, you have access to a debugging interface, including Spark History Server, the Yarn Timeline Server, and Tez UI. These are fully serverless. You don't have anything to manage. And because EMR offload the logs on S3, that also means you can access the logs and debug the applications of terminated cluster. So one of our customers who is using EMR Studio is Verana Health. They were able to really reduce the cost and reduce also the development cycle using this unified interface, and they really improved their Jupyter Notebook experience. Another example is Mapbox, and they are using EMR Studio to prototype Spark application and data science models. And again, using this fully integrated development environment, they were able to really improve the experience of their data scientists and data engineers. SageMaker Studio is also very popular for notebooks, and especially for data science, for training model, doing some data preparation. You can also plug and integrate EMR with SageMaker Studio now. And you can run, for example, Spark, Hive, and Presto jobs on EMR for data science, things like training model, data preparation. The idea is really to leverage the benefits we previously discussed on the cost and the performance. Like, for example, if you want to use Spot instances or Graviton instances, you can just offload the processing of your job to EMR. So directly from SageMaker Studio interface, you can also discover and connect to existing clusters. You can run Spark, Hive, and Presto from this interface. You have also access to the same debugging tools that you are familiar with. And finally, you can also manage your cluster from SageMaker Studio. You can create, scale, and auto-terminate clusters. You also have access to these templates using Service Catalog. So that was an overview of data science. Let's move now on the new deployment options that allows you to run Spark job on Kubernetes. We launched this year. Amazon EMR on EKS is really useful to consolidate your workloads. The idea is really to simplify the infrastructure management. There is no more cluster to manage in EMR. You just rely on the EKS resources to run your jobs. And because your workloads are isolated in containers, that's really simplify also the management of multiple versions. So you can consolidate multiple Spark applications using different versions. It also facilitates the lifecycle management of your application and the upgrades. And very important, you still have access to this Kubernetes API and all the features associated with it. You can implement various solutions like multi-AZ resiliency, using, for example, worker nodes across multiple AZ, but you can really customize your deployment. This slide is a good example of the consolidation you can achieve with EMR and EKS. So on the left side, you can see a typical example with EMR and EC2. You have multiple EMR versions. You basically need to isolate them on different clusters, and you can waste some resources doing that because you are not fully utilizing the cluster and the resources. With EMR and EKS, you can really achieve very high consolidation for both multiple Spark version and EMR versions, but also between your analytic workloads and the other workloads. And the good point is you do not sacrifice security doing that because you can still provide an execution role per workload to ensure that each job, even if they are using the same instance and the same workers, each job will have its own set of permission to access the resources. Running job is very easy. You don't need to learn new tools. You can just use the EMR Containers API that is available in the CLI and the SDK. We have seen that you can also run EMR Studio or self-managed notebook. And it's also integrated with your orchestration tool. So if you are using Apache Airflow, we provide an operator and a sensor to connect your Airflow pipeline with EMR on EKS and submit your job on EMR on EKS. And if you are using step functions, you have also this native integration. You don't need to code any Lambda. You just need to integrate using the step function language. This is an example of the EMR Containers API. You can see that it's very simple. In green, you have the EMR parameters, like the version, the execution role. And in yellow, you have the very common Spark submit parameters, which are exactly the same, like Spark executor configuration and Spark driver. You can also customize your workload using EMR and EKS. One of the features that allows you to do that is the custom container image. So for example, if you want to package dependencies to accelerate the startup of your jobs, you can customize the image, or you can also maybe provide multiple base image for different type of workloads. Or you want to integrate with a CI/CD pipeline and use some custom validation tools, vulnerability scan. You can do that very easily. You just pick the base image from EMR. You build your own image. You publish it on ECR registry, and then you can consume from all your jobs using this ECR image. Another option to deeply customize your deployment is to use the pod templates that is natively supported by EMR NIKE. Pod template is a Kubernetes feature that allows you to customize pod definition to really achieve very granular placement, for example. If you want to optimize the price performance, you can select the workers on Spot or Graviton. You can also decide which level of consolidation you want to achieve. You can isolate workloads. You can consolidate workloads. You have lots of flexibility. You can also implement the sidecar pattern. For example, if you want to take the logs from your Spark executors and drivers, you can schedule a container that will run alongside your EMR containers, get the log, and send it to a logging infrastructure, for example. The other pattern that you can implement is the init container. If you need, for example, to download or install any dependency when you start an EMR job, you can do that, precising a small container that is triggered at the beginning of the job. Stitchfish is one of our customers who is using EMR NIKE. They migrated from open source Spark on Kubernetes, and they were really able to really achieve very high consolidation, both multiple Spark versions and Spark workloads with other workloads. Another customer is Rivian. Rivian moved on EMR NIKE to scale their near real-time processing, and they were able to follow the demand from their research and development, which was expecting a lot of vehicle test and battery test. Okay, let's now see how Amazon EMR can simplify the building of data lakes. And for that, I will take some very generic example to really explain the challenges that you can have and how EMR can solve that. First example is a streaming ingestion. You are ingesting thousands of records from Amazon managed streaming for Kafka. You need to process them using a Spark streaming job on EMR and write it to S3 to expose to some users. You can have some writing challenges, like atomic change. You don't want partial results. You also want this reader-writer isolation to provide consistent query output. You probably need also high-throughput ingestion to adapt to a spiky workload. And with low-latency job, you probably already had this small file issue that really decrease the performance on the read side. So you need to compact them. And if you have multiple jobs, you also need to handle concurrent writers. Maybe also you need to optimize your data set for consuming, and you need to, common optimization is clustering, for example, so you need to provide more optimization for more type of queries. On the query side, you probably have some data analysts that would like to query the data, the latest changes of your data set, or they would like to have a specific value for records from another point in time. And they may want to use their favorite query tool or the right tool for the right job. So they are probably using Presto, Hive, and Spark SQL, and maybe Amazon Athena or Redshift Spectrum. So you need to integrate with all these tools. Another example is the CDC ingestion pipeline. You are ingesting some data from a changelog in an operational database, like Aurora, using AWS DMS. And then you have this Spark job that processes the data and write to an analytics tier. So in that case, you have similar challenges, but you also need to support the row-level upsert and delete, because you need to propagate changes from the source into the target. And you also need to, of course, cluster by secondary keys, because you need to optimize this workload for consumers. Finally, for GDPR pipelines, you probably have a monthly batch that takes the request, the deletion request from your users, and you go through the entire data set to delete the records, the corresponding records. You need to support update, upsert, and delete, of course, but you probably also need to handle the concurrent writers because you don't want to interfere with the production job. So this is where Apache Hudi can help. Okay, it's an open file format, an open source file format that enables transactional data lake, and it's natively supported in EMR. So on the ingestion, it provides ACID transactions, it provides record level upsert and delete, high throughput ingestion, automatic compaction of small files. It's also integrated with the most popular framework for streaming, Spark and Flink. And in latest version available on EMR, the Hudi 0.9, you also have support for Spark SQL DML. On the query side, it's widely supported in the open source community. You can query Hudi dataset via Spark, PrestoDB, Trino, and Hive. You have these performance optimizations because it's using metadata and indexes. And you have support for incremental and time travel queries. On the administration side, it provides lots of automation to optimize your data sets. You have this asynchronous background compaction. You can also asynchronously optimize using sorting and clustering. It automatically cleans up the old versions. And finally, you also have access to critical metrics like commit and rollback to understand what's happening into your Hudi dataset. So Hudi is integrated in EMR. And one of the best examples is the availability of Hudi metrics and the key metrics directly into CloudWatch. So you can, for example, monitor the number of commits and the total records written in the Hudi dataset directly from CloudWatch. It's not only integrated with EMR, it's also widely supported in AWS. You can, for example, catalog Hudi datasets. You can implement glue jobs on Hudi datasets. It supports also AWS Lake Formation for fine-grained access control. And you can query it with Athena or Redshift Spectrum. It's also integrated with DMS for CDC ingestion, and we have seen that you have metrics directly in CloudWatch. Let's now move on the latest security features that we added in EMR to support various patterns. This is a brief overview. I will go into the details. EMR already has a comprehensive set of security features. So if you want to isolate your workloads, you can use VPC, private subnet, and security groups. You can also set authentication through LDAP and Kerberos. We have seen with EMR Studio, you can use SSO, but you can also use IAM. For the authorization, you have this cluster IAM role, one role per cluster. And you can also use Apache Ranger for fine-grained access control. We are extending these authorization features with the support of user execution role, which allows you to trigger a job with a specific IAM role. And we are also extending with the support of lake formation for fine-grained access control, both in previews. For the encryption, support encryption at rest and in transit. And for the audit, if you are using Ranger for fine-grained access control, you have these audit capabilities. But now, because we are also integrated with lake formation, you can use CloudTrail and lake formation audit capabilities. So let's go into the details of what you can implement. This is the traditional approach with the IAM cluster role. So you basically set up an instance profile for your cluster. And if you have multiple users with multiple roles and different permissions, you basically need to isolate them on different clusters. With the user execution role, you can now create multi-tenant and shared clusters. You can have a single shared clusters, and you can submit jobs. So for example, in this case, the user 1 will submit a job with role 1 to access stream 1, bucket 1, and table 1. User 2 will submit a job on the same cluster, providing the role 2 to access stream 2, bucket 2, and table 2. We are also adding the integration of lake formation to support fine-grained access control. We have a lake formation permission model. Lake formation has a different approach. Okay? You are not setting permissions for the object on S3. You are really setting the permission for the data. You are setting permissions for databases, for tables, for columns, and even for rows. So now if you mix the user execution role and lake formation, fine-grained access control, your user 1 can pass a role 1 to this multi-tenant shared cluster. Lake formation will apply corresponding permissions, for example, access to table 1 and all the columns from 1 to 10. User 2 can pass role 2 to the same shared cluster, and then lake formation will apply different permissions at the column level. So for example, it will just restrain the access to column 5 to 10. So that's a very flexible approach, mixing execution role and lake formation access control. You can now really implement shared clusters and provide deep control on the permissions. The typical use case is for SaaS application, where our customers need to provide different and fine-grained control, different access to multiple users using the same resources. So that was a brief overview of the features we delivered to Amazon EMR to ensure that it remains the best fit for your analytical workload and big data workload. If you want to know more about the features we covered today, we have lots of deep dive sessions on each of them. And if you have any question, please feel free to reach out. We love working with customers. Thank you.